after we have mounted a chip, we must interconnect it electrically. Typically, the top side of a chip is carrying the circuit, and that circuit must be connected to a lead frame or to a substrate. And for that purpose, there are different processes which we can use. And one of the first processes to make many parallel interconnections is wire bonding. What we can see here is so-called ball bonding, or it is also called nailhead bonding. So that is a demonstration image by a Japanese company which provides bonding wires, which is the Tanaka company. These bonds are very beautiful. It depends on the quality of the wire material and also on the quality of the bonding machine. On the other hand, the other properties which we can see on that test chip are definitely not so good. Here, that structure, we have a hollow edge here of the chip. We have a crack here. All that is not so good and normally not tolerated in an electronic high-quality production. But here was only the demonstration for the wire bonding, and that was good. The diameter of the wires is 25 micrometer, and the wires consist almost completely of gold, so only slight impurities of other elements are added here. And it is also important to have a very high uniformity of the wire bonds. And uniformity also guarantees that there are not very many defects. So typically, in a production, we talk about wire bond defect rates. So imagine we would produce 1 million wire bonds, and then we could have a defect rate between 1 and maybe 10,000. And that 10,000 ppm is a probability of 1%, and that is 1 in a million. And now imagine if one wire bond on a circuit is defective. That will lead to the fact that the complete circuit is defective. There is no possibility for rework. So if you have one wire bond and that doesn't work, the circuit will not work, and you throw away that circuit. Now imagine we would look at the yield per module which we produce. For instance, we have a module which has 100 wire bonds, which is a relatively small device. And now, depending on the yield or the defect rate per wire for the wire bonds, we can say if we have a 1% chance that we have a failure in a wire bond, then the yield of the module is below 50%. If we want to have a yield which is roughly, let's say, 92%, we need a defect rate of wire bonds which is only 1 promille. So 1 out of 1,000 bonds may be defective. On the other hand, if we would have, for instance, only a wire bond defect rate of 100, then we could have a yield of 98%. But with 1,000 wire bonds per one module, we would only have a yield of 92%. Going to some special applications, for instance, 10,000 wire bonds, that is sometimes needed in special sensors, for instance, in the LED in the LED line of a laser printer or such a thing, then we have very many wire bonds in parallel. And here, in order to have a yield of 90%, we must have a wire bond defect rate which is 10 ppm or lower. So imagine you have to produce 1 million wire bonds, and only of these 10 wire bonds must be are allowed to be not okay. So that's quite demanding, but that's more or less state of the art in good production. Also, the formula, we could say the yield of the module is 1 minus the defect rate of the module. And so you could also say, if you have the yield of the bond and take it to the power of n, which is the number of bonds, that's the yield of the module. And in that way, you can easily estimate what your wire bond defect rate must be, or a maximum boundary for that defect rate, if you want to have a certain yield. And the yield is very important for the questions, will you be successful on an economic scale or not? Now let's have a look at the individual processes. So in a bonding machine, the part which performs the bond is the tool. And there are two principal processes, wedge bonding and ball bonding. In the wedge bonding, we have a tool, and that has a hole through which the wire comes, and the wire comes under a relatively small angle, for instance, something like 30 degrees. Here we have some kind of foot which presses the wire onto the substrate. So we have pressure here, and the second thing which is important is we have vibration here. That is an ultrasound vibration. We are talking here about 1 micrometer or so, no more. And that vibration is already sufficient. It leads to a certain friction, and under that friction, the material of the wire, which is typically aluminum, and the surface here, which is also aluminum, will be welded together. It's a process which is at relatively low temperature. There is no fusion or melting in that process. After we have performed the first bond, the tool is moved, and we have the second bond, touch down, ultrasound for a very short time, and finally the wire is broken off near the bond, and in that way we can form a loop of that wire. That process works out fine. Typical diameter is, for instance, 25 micrometer of aluminum silicon alloy. That is a version of that process which is using pure aluminum. That is a so-called heavy wire bonding. The wire diameter here is 0.3 millimeter. Also, we have such a wire bonder in the clean room. And what is interesting here, it is performing so-called stitch bonding. So we have the first bond move to the second location, to the third location, to the fourth location, and to the fifth location. So it's more like a sewing machine than just a bonder. And in that way, it is again a very efficient process which connects, for instance, transistors and diodes, which are on a on such a copper alumina substrate. Here is something more of a detail of such a bond. So when we look at such a bonding location, we can use a SEM, and here is a severe problem. For instance, here we can see a crack. The trick in the bonding is that there is a heavy deformation in the bonding wire. Unfortunately, when the deformation is too high, it forms a crack. So you could say the stronger you bond, the stronger this interconnection will be until you reach a certain limit, and from that limit on you form cracks in this heel region, and that will degrade the strength of such a bond. So it shows us there will be an optimum bonding condition. Here is a modern bonder that's also for thin wire bonders. Here is the tool. Here is a so-called sonotrode. That's some kind of a horn which directs the ultrasonic vibration into that direction. And so in that way, the tool will move here, but again, it's only a micrometer. Such bonders are highly automated. Such bonders also have a vision system. So we see this for illumination. We have LEDs, and that system will find precisely the bonding pad. So it is programmed in a way it will not go to a certain position, but it will go near the position, and the fine-tuning to find the target location is done by that automated system. So typically, we can produce something like 6 wires per second in such a bonder, and the accuracy of placement of such a bond is somewhere around 5 micrometers. So that is really a precision machine, and the ultrasound frequency is typically 100 kilohertz. So here is that horn. Here you could say here by some piezo material or by some magnetorestrictive material, you produce an ultrasound wave. So you could say you have that wave. It has a higher and higher amplitude, as we can see here, and finally, so here would be the wire, and finally that tip where the wire is placed is moved with the amplitude. So that's more or less the heart of that bonder, but it's rather one of the cheaper parts of a modern bonder. Now let's have a look in more detail at the process parameters. And the process parameters are the force which you press. The second is the time for which you bond, and the ultrasonic power. which gives us a certain amplitude. So here, when you touch down, you could say here is just the touchdown. The force which you put on the wire is still low, but it increases with more and more touchdown. At the same time, you can see the individual steps from the time when you have touched the surface. That shows us more or less how the wire is compressed more and more. And at that time, we turn on the ultrasonic power. And then we see by the superposition of the ultrasonic deformation and the previous deformation, we have a strong increase. So the tool is going down, the wire is deformed in a way, and during that phase we both have a friction between the wire and the metallization, we have a bonding, and in the end we also have a strong deformation of that wire. In fact, you could say most of this bonding time is not necessary. We could have stopped the process here. That was only for us to look what happens afterwards. A second process, which is very important in integrated circuits especially, it's ball wedge bonding. Ball wedge bonding is different. You have a ceramic capillary, and from the tip of that capillary comes the wire. So when you look at it, it's a little like you have that that internal part of a ball pen, where this this writing rod comes out of the ball pen housing, and so in that way, that's a concentric assembly here, and the wire looks out a little, and now we want to form a ball, and that is done by remelting it. That's typically done by spark discharge from a capacitor, and so the wire will melt. Spark discharge has the advantage that you can control the energy very well, and in that way you can also control the size of the ball, because that's important. If the size would be always different, you would not have a uniform quality of your bonding. The first bond, the nail head, is in almost all cases performed on chip. The reason is this nail head distributes the force of the bonding very well on the chip, and so you avoid cracks in your chip. After the first bond has been accomplished, the tool is moved in a certain way. We form that loop, and then the edge of that tool is used to form the wedge bond here. So that's the reason why the wedge bond and the ball bond in ball bonding are quite different. And also typically the ball bond is always much stronger than the wedge bond is. After that wedge bond, again, the tool is lifted, and we have a certain braking operation, so we get a loose end of the wire again, and then the whole game starts again at number 1. And in that way, we can produce 1,000,000 bonds. Here we see such a wire with the ball which has been formed. One of the problems is that the wire typically has a fine-grained structure that is harder and stronger. That ball is soft. That is also not a problem because the ball is big, so also it is softer. It has a larger volume, so that makes it stronger. But this area here, the heat-affected zone, that's also soft, and so often we can get some fracture at the neck of such a bond after the nail head bonding process. Here again, that's just the principle. This Tanaka company, they did a special etching process, so we can see the individual crystals which form this wire. So each of this polygonous structure is a small gold crystal we have in here. If it all goes well, we can see it here. That's a Hall sensor. That looks nice. The die attachment is nice. We have no cracks on top here. The bonds look uniform. We can even form some kind of corner in the bond, and here is again the wedge part, and here is the ball or nail head. Part of that bond. And what you can see here, that's the lead frame. Now, that looks so simple altogether, but in fact it is not. One of the problems is the metallurgy of wire bonds. When we look at the phase diagram, we have to regard aluminum because that's the metallization, and the gold because it's the wire. What's the initial reason we use gold for the wire? The main reason is we can make nice balls by this remelting process, and these balls can be very uniform, and the melting temperature is also not too high for that gold. But now look at the binary phase diagram here, and so we can see we have the intermetallic phase gold aluminum 2, we have the phase gold aluminum, we have gold 2 aluminum, we have gold 5 aluminum 2. Also, it's not quite sure it has that composition, and we also have gold 4 aluminum. So all of these are phases which we could expect in our welded series between gold and aluminum. Let's have a look here. I would not be able to say what it really is, so it's something like gold X, aluminum Y, for instance, gold 2 aluminum, gold 5 aluminum 2, or gold 4 aluminum on the Hall sensor. If these phases are too thick, they become brittle. That's not good for the strength of that bond. If these intermetallics are limited, they increase the strength of such a bond. So the image is not very sharp because it was taken with an optical microscope, and that microscope is at the limit of its optical resolution. In other cases, we can form a phase which is gold aluminum 2. That is only formed when we use aluminum wire on a gold conductor, for instance in thick film or thin film technology. And in that case, when this phase is formed during the bonding process, it will be extremely brittle, and the formation of that purple phase is the so-called purple plague. So purple plague means you really have a severe problem, and your interconnections, they probably will die when you put the slightest pressure on them. One of the things which is important, if the gold is very pure, it's not a problem. It only happens in a system where we have much aluminum, not much gold, therefore this gold aluminum 2, and when at the same time the gold is contaminated. But now let's have a look at the energies in our gold process. So ball wedge bonding can be performed using temperature, pressure, and time. So we have the ball, it is just pressured at elevated temperature onto the chip for a certain time, and that gives diffusion and gives a bond. That's so-called thermocompression bonding, and only used for thin wires of gold when you have a ball. On the other hand, you can add ultrasonic power. The advantage is the process is safer, so it is less sensitive against contaminations and so on, because the ultrasound has a cleaning possibility. Also, the ultrasound has a similar action, like you would increase the temperature in your process. So here in the thermosonic process, which is state of the art in IC, we have ultrasonic power, temperature going maybe up to 300 degrees centigrade, typically maybe 200 degrees centigrade, and in that way it is a process which works very well with a high yield. Again, here we can use thin wires, but only ones where we can form a ball. So we can never use aluminum, but we can form balls from gold, platinum, palladium, and copper under nitrogen atmosphere. We can also perform this process with a wedge bonder. Again, we have the similar properties. And what is also used in thick wires is just wedge bonding with only ultrasonic power. So we have ultrasonic power, pressure, time, but no temperature. So that's a cold process, and that is mainly done for thick aluminum wires or for very thin wires of aluminum silicon 1. In that way we have a certain system, but let me mark it. So you could say typical is wedge bonding with thin wires. We have wedge bonding also with thick wires, and on the other hand we often have ball wedge bonding with, in most cases, thin gold wires. That are the most frequent combinations. No, I did a mistake, of course. It's thermosonic with thin wires. That process is not so frequent anymore. So these are the mainstream processes we can find in wire bonding. Okay, here to give you some examples, that's a tool for wedge-wedge bonding. So could say here the wire will come, and then here it is bonded onto the substrate. Here you see such a bond, and here are these loops. What is important in this bonding process, you cannot go away to any direction, but you always have to bond into the direction of the wire. On the other hand, if you have such a symmetric round tool where the wire is coming here with the ball, then you can do the first bond and you can go into every direction. And that's one of the reasons why ball wedge bonding is a little faster than wedge-wedge bonding. Okay, so we can compare both processes. I would say the main difference is that is mainly for IC, microelectronics, and that is more for hybrid circuits. So that's the main target fields we have here, and of course it's also mainly for power if it's a thicker wire. So on the other hand, both processes are frequently equivalent, but aluminum wire cannot be used for high temperature electronics. Okay, here are more advantages and disadvantages. I recommend you read it for yourself.